Hello all and welcome to this next session of the course Pre-MBA Statistics or Pre-Business School Statistics. So again, just to give you a short background as to where we are at, so maybe in the last session we talked about a few plots, few charts, more from a descriptive sort of an angle, and then we sort of talked about a couple of measures of descriptive statistics such as sample mean or the sample median. So in the beginning of today's session, we'll delve slightly deeper and we'll talk about a couple of other measures. The first one which you see is called as a sample mode. Now again, what exactly is sample mode? Now again, the idea behind discussing all these measures is to sort of have a descriptive idea about whatever practical data set that you have. So analyzing that and finding, let's say, either the mean or the median or the mode or let's say variance or standard deviation, which we'll discuss very soon, is kind of a key so that you have a background about the behavior of the sample or the behavior of the data set. Okay. Alright, so we'll spend some time on sample mode and then we'll move ahead. So sample mode is what? So sample mode is nothing but another statistic which has been used to indicate the central tendency of a data set and is defined as a sample mode, which is by the way defined to be the value which occurs with the highest frequency. So again, you may pause the video and then sort of think that when we talked about a frequency table or cumulative frequency table and those ideas, then you have different values and the corresponding frequencies which are corresponding to those values, and simply you find out that value which has a highest frequency or greatest frequency, alright, and then that value will be called as a sample mode. And then we will see a small example also, don't worry. Now, if no single value occurs most frequently, then all the values which occur at the highest frequency are called modal values. So, in that case, there will be more than one sample modes. Okay, so again we will talk about a simple example. So, you have a simple table, the first column gives you age and the second column gives you the frequency. By the way, you have a small typo here. So, let us say you have the following table gives the values obtained in, let us say, certain number of sample sizes, and then the data set here is not rolls of a dice, my bad, but then you have ages of different people and the corresponding frequencies, alright. So, you have 9 people having age 1, then let us say, yeah, by the way, this is an example of rolls of a dice, and then the error here is kind of not the age, but then you write down dice here, okay. So, small typo, so maybe this is not a typo, by the way, so maybe you can erase this, and then the first column gives you the roll on the dice. So, 1, 2, 3, 4, 5, 6 if you see, and then the corresponding frequency. So, the roll of a die and then the value being 1 in the top face occurs 9 times, then 8 times, 5 times, etc. And overall the sample size n is nothing but 40. Okay. So, now just by observing this idea, so can you find out all these things, sample mean, sample median and sample mode? Now again, in this session we will not spend time on finding the first two, sample mean and sample median, since we have discussed in the last session. So again, if need be, you can go to the last session and then get an idea about how do you find out sample mean and sample median. But talking more about sample mode, so can you tell me which value occurs the most, or rather which roll of a die occurs the most? So one can clearly see that the number 1 occurs the most because the frequency is highest, which is 9. And hence the mode of the data set is nothing but 1. Make sense? So, it's as simple as that. So, do not try to complicate things. So, whichever number, whichever observation occurs the most or has the highest frequency in that frequency chart or frequency table, that value would be nothing but called as the sample mode. Right? Okay, so now that we have talked about number of measures such as mean, median, mode, which sort of measure the location of any data set, now we will spend very brief time on what do you mean by sample variance. Okay. So, on the other hand, sample variance is nothing but a statistic which describes the spread or variability of the data value. So, rather than giving you location or a central measure, a central tendency value, it sort of tells you that how spread the observations are or how variable the observations are. Okay. Now, this statistic measures the average value of the squares of the distances between all the observations and the corresponding sample mean. So, we will talk very briefly about this formula here. It is a very standard formula to calculate the sample variance, and then is denoted by S square, and S square is nothing but given by summation xi minus x bar whole square divided by n minus 1. So again, in the previous example, since n was 40, you will have 39 in the denominator, and then what you do is you take each and every value or each and every observation in the data set, you subtract the sample mean from them, take the whole square, and then take the sum. So now can you have a sense about why exactly sample variance measures the spread? And again, the answer should be quite evident, because what you are doing essentially here in this formula is taking nothing but the deviations of all the values from the sample mean. Okay, so if you are kind of taking deviations of each and every observation from the sample mean of the data set, you will kind of measure the variability in the data set. Okay. So again, just to summarize, sample mean and sample variance. Okay, so sample mean and sample variance, these are kind of standard measures to measure location and the spread of the data set. Okay, so again you have two different sort of data sets here. So data sets A and data set B. So the first one is 3, 4, 6, 7, 10, and the second one is minus 25, 15, 24. So kind of straightforward examples, but then the question is find the sample variance of the data sets A, B. Okay, so you may pause the video, you can try to find out the variance and then get the answer. Okay. Now again, nothing much to discuss here. This is just an alternative form in which we can write down this guy, summation xi minus x bar whole square. So again, if you remember, we had this structure in the sample variance formula. So alternatively, how can you express the same constant? So you have a small proof here. So again, we will not discuss each and every row, but you can pause the video and then try to sort of understand what is going on. So the only thing we are doing is trying to open the whole square term, then taking the summation inside, simplifying things, and then the last thing is this guy. Okay. So alternatively, I can actually find out the sample variance as nothing but summation xi square minus n x bar square. And again, what is x bar in all these notations? So x bar is nothing but the sample mean. Okay. Alright, so now a small example. So the following data gives the number of fatal airline accidents of commercially scheduled air transports during 1985 to 1993, and now the question is find the sample variance. So all these are the values. So the very first thing is to find out the sample mean, let's say, of all the observations, right? And once you get hold of the mean, you subtract the mean from each and every value here, and then take the whole square and then sum, and then finally divide by n minus 1. Okay. Alright, now the last measure sort of we'll discuss in the first part of today's session is called as sample standard deviation. So again, I'm very sure that you must have heard about all these terms, so variance, standard deviation, etc. Now simply put, standard deviation is nothing but square root of variance. Okay. So again, if you see the formula is denoted by S, because earlier variance was denoted by S square, so standard deviation would be S, and then this guy is nothing but the under root or square root of sample variance. So what you have inside the square root is nothing but variance, or rather sample variance. Okay. So just another way of representing the deviation or spread or variability in the data set. Alright, so probably now we are in more stronger position to sort of look at a couple of practical examples. Again, understanding from a theoretical point of view is kind of okay, but the key is to sort of how do you apply that to real world setting, or how do you sort of analyze the real world data. So we'll talk about a couple of examples from different angles, and it sort of combines all the knowledge or all the sort of lectures or points we have done so far. Okay. So practical examples using a few case studies, and then here we'll focus on one particular data set containing some variables, some features, right? And then we'll try to find out that how can you sort of answer some research questions. Okay. Okay, so now just to measure or sort of just to give you a brief background about the data set. So the first data set we'll talk about is called as growth of orange trees. Okay, so it's a simple data set and then available in R also. So growth of orange trees. Now what this does is the data set contains records of growth of orange trees. So it's sort of you have number of orange trees, and then the data set contains records of growth of the corresponding orange trees. And then the following variables of interest are present within the data set. So the first one is tree, and then what does tree do? So tree is nothing but an ordered factor indicating the tree on which the measurement is made. So imagine that you have number of trees. You don't have just a single tree, but you have number of different trees, and then each tree is sort of denoted by a number. So 1, 2, 3, 4, etc. And then we'll soon see a snapshot of a data set, and then you'll understand better. But then you have, so imagine you have number of trees in this entire data set, and then each tree is sort of an ordered factor indicating the tree on which the measurement is made. And how exactly is the ordering being done? So, ordering is according to increasing maximum diameter. So, for example, the tree ordered with a number of 1 would have the least maximum diameter. So, the tree ordered with number 2 would have slightly more maximum diameter, and so on. Then the second variable of interest is age. So, a numerical vector giving age of the corresponding tree starting from 31st December 1968. So, this entire growth of orange trees data set is not very recent one, but then it sort of tells you an idea about how the trees or rather how the orange trees are growing, then what exactly is the age of the tree. And then third variable interest is circumference. So, numeric vector of trunk circumference. Okay. So, just we will focus on these 3 variables essentially. So, an ordered factor of the tree ranging from, let us say 1, 2, 3, 4, 5 and so on, then the age of the corresponding tree and the corresponding circumference, which gives you the trunk circumference in millimeters. Okay. Alright, so this is exactly how a snapshot of the data set looks like. Now, it contains 3 columns as described just a short while back. So, the first column gives you an ordered factor of the tree, and here you can clearly see that you have 1, 2, 3 and so on. So, by the way, this is not the entire data, like I said, this is just a snapshot of the data. You have more number of rows in the data set. Okay. But then the second column gives you the age, for example 118, 484, and by the way, this age is nothing but in days, and in the previous slide you saw the starting date, right. So, 31st of December 1968. So, for example 118 days means the first tree or rather the first row in the data set has an age of 118 days, and similarly 484, 664, 1004, 1231 days, etc. And lastly, the third column gives you the circumference or rather the trunk circumference in millimeters. So, 30 millimeters, 58 millimeters, 87 millimeters, etc. Okay. So, again a small suggestion to all of you is that you may pause the video at any time, just gauge on the data set, try to seek some inferences, what is going on, right, and so on and so forth before you sort of proceed to formal analysis. Okay. Okay, so now the first question is growth patterns by age. So, is there any way to sort of answer this sort of a research question? So, growth patterns by age. So, firstly, what do you mean by that? So, analyze how the tree circumference changes with age across the different trees. Okay. So, the focus is more on, let us say, analyzing how the tree circumference changes with age. Okay. So, you are sort of focusing on 2 columns, circumference and age. So, and then we want to sort of answer that how the circumference changes along with the tree age across all the different trees. Okay. So, again you may pause the video, you may think that what could be a solution or rather how to approach with the solution and so on and so forth, and then we will show you one solution here. So, the very first thing is a visual sort of a solution. So, what one can do is one can create some simple line plots of circumference versus time. So, you can create a plot where you are sort of plotting the circumference over time, and then time means what? So, time means nothing but days since planting of the tree for each tree, and then simply compare. Okay. And then this is exactly how things would look like. So, the title is orange tree growth over time, and by the way, like I said a short while back, that in the entire data set you have 5 trees. So, can you see that here? So, 1, 2, 3, 4, 5. Okay. And then again, like I said, so what do you mean by 1? So, 1 means the least maximum diameter, 2 means slightly more, 3 means slightly more, and 5 means the trees with maximum diameter. So, this is essentially how the ordering has been done in the data set. Okay. But now the more important part is, so each tree has a different curve or different line plot or different path over time. So, by the way, x axis contains age in days. So, 400, 800, 1200, 1600, etc., and the y axis measures the circumference. Okay. So, very clearly just by looking at this plot, can you tell me that which tree has a largest growth in terms of circumference over the time period? So, the answer is 4, isn't it? Because the blue line, if you see, blue line sits right at the top there. So, as in how the trees corresponding to code 4 approach more or rather they age out, let us say 800 days, 1200, 1600 and so on. So, as in how you move across the timeline here over the x axis from left to right, the circumference of blue trees have the largest growth. Okay. And as compared to that, the circumference of the green trees, now which ones are the green trees? Green trees are nothing but 3, where you have code to be 3. Okay. So, circumference of the green trees are not growing that much because the green path or the green line plot sits at the very bottom. Okay. So the maximum sort of circumference of the green trees rises up to, let's say, somewhere around 150 millimeters. As opposed to that, the maximum circumference of blue trees having a code of 4 sits somewhere around slightly more than 200 millimeters. Okay. So things can be as simple as this. So need not complicate things. I mean, just based on simple line plots for corresponding trees and their circumferences, we can sort of study the path or the evolution of the growth of orange trees there. Okay, so now a second point is compare whether trees grow at a similar rate or if some show faster growth spurts, etc. Isn't it? So let's say what we can do here is that, let's say again the same things. On the x-axis you have age, on the y-axis you have circumferences, but this plot is a slightly different plot. So what we have is, rather than plotting all the 5 lines on a single plot, we have one plot for each tree separated out. So can you see that? So the first row here, rather, or the heading of each subplot gives you the tree. So 1, 2, 3, 4, 5, and each tree you can actually see the corresponding circumference corresponding to the age. Okay. Now again, one can actually make some very evident conclusions. For example, the tree 2 and tree 4, they sort of show more growth, right, as compared to, let's say, tree 1, tree 3, etc. And then tree 5 is sitting somewhere in between there. Okay. So things can actually be handled in a slightly different manner, but again the conclusions are kind of same, that the trees 2 and 4 sort of show slightly more growth as compared to trees 1 and 3, and again 5, like I said, is somewhere in between trees 1, 3 and 2, 4. Okay. So again, what is the crux of the matter here? So crux of the matter here is that a single problem could be attacked using different solutions coming from, let's say, different angles. So one can actually have, let's say, all the line plots in a single graph, or I can sort of have separated plots which can actually tell you slightly more, because you can so some people might visualize the growth of the trees slightly more clearly as compared to if you have all the plots in a single graph. Okay. Alright, now the second point in the same case study, orange tree case study, is that distribution of tree circumference. Okay. So what do you mean by that? So at the time when data was collected, what exactly is the spread of tree circumference across all trees? So now the focus is slightly different. So at the time when data was collected, what exactly is the spread of tree circumference across all the trees? So now we are kind of more keen in finding down the spread of the tree circumferences. So essentially, what is the circumference across all trees at the time when data was collected? So what could be done here? So how could this problem be attacked? So I can actually have a frequency table of circumference at the day 1004. So why this day? Because in the question, if you look carefully, it says that at the time when data was collected, right? So at the time when data was collected means in the very last observation. So at the day 1004, I can actually get a frequency table of all the circumferences, and from that frequency table, I can sort of gauge as to which tree has slightly more circumference as compared to the other. Okay, so this is exactly what we have. So let's say you create all these ranges, alright, and by the way, all these ranges corresponding to ranges of what? So ranges of circumferences. So circumference, let's say between 30 to 50, 50 to 70, 70 to 90, all the way up to 190 to 210. And by the way, again remember the unit of circumference is millimeters. So 30 millimeters to 50 millimeters, etc. Okay, so I can sort of create a frequency table, but then one idea is to create ranges rather than have all the single circumferences. Okay, and then as usual, the second column could be a frequency sort of a column which tells you 6, 4, 3, 1, 6. So for example, what do you mean by 6? So you have 6 such trees having circumferences between 30 millimeters to 50 millimeters, and at what time? At the point of 1004 days, or the very last observation collection, and so on and so forth. So you only have one such tree where circumference falls between 90 millimeters to 110, etc. Okay, so again what we have done, so we have created a frequency table of circumferences at the day 1004, and now the moment you have any frequency table, the next thing I can easily do is to plot a histogram of the circumferences, isn't it? So I can actually plot a histogram of all the circumferences, and then let's see that how the histogram looks like. So this is exactly the histogram of all the circumferences frequencies across different circumference values. Okay, and again as you can see that, for example here, so here there is no tree here. Okay, so somewhere between, let's say, 180 to 200 millimeters there is no tree, and then can you tell me the circumference range where you have more trees? somewhere here, right? Because this is the highest bar. So somewhere between, let's say, 100 to 110 millimeters or 120 millimeters, you have more number of trees. Okay. So such simple solutions or rather simple conclusions can be drawn based on a frequency table, the corresponding histogram, etc. Okay, so now the third problem, the same case study, is let's say early versus late growth. So what do you mean by that, early versus late growth? So now the question is that do trees show more rapid growth in early stages or later stages? Okay, so let's say if you are sort of analyzing a growth of, let's say, a single orange tree, then do you see more rapid growth in, let's say, circumference or diameter, etc., in the early stages of the tree when the tree is just growing, or slightly later stage? Okay. So how about that? So how can you sort of give an answer to such a question? So now what we can do is we can sort of calculate the average increase in circumference values between, let's say, a few successive time points. Okay, and what successive time points? So initially I can take 118 to 484 days, which is on the lower end of the spectrum, because again remember what the question is. So we are kind of focusing on early stages and later stages. Okay, so 118 to 484 days corresponds to early stages, while 1372 to 1582 might correspond to late stages. Okay, and in both these groups the idea is to sort of find out the average increase in circumference between successive time points. Okay, so 118 to 484 days and 1370 to 1582 days. Okay. So now we will see that what happens. So again, the first column gives you all the different trees, and again if you see here, for each tree from 1, 2, 3, 4, 5, we have two instances. The first instance gives you early, second gives you late for each tree. Okay. For example, let's say early, and then again it tells you that what do you mean by early. So again, as seen in the last slide, 118 to 484 days, and then late means 1372 to 1582 days. Now if you focus just on the first tree here, the first two rows, the mean growth in the early part is 28 millimeters, while the mean growth in the later stage is just 3 millimeters. Okay. So just by looking at the data for the first tree, can you tell me that which phase do you see more growth? Of course early, isn't it? And this conclusion is sort of consistent even if you go down the levels of trees. So the second tree, the same thing. So 36 0, 21 1, 35, 19 3. And again this idea is kind of intuitive also, right? I mean, as and how the tree is growing, the growth would be kind of more during earlier days rather than once the growth is full, isn't it? So earlier growth would always be more than the later growth, and this is clearly what you can see in all the tree codes and the different phases there. Okay. All right, and then visually, if you want some visual plot or visual graph, I can actually have a result in a bar chart comparing early and late growth. So for each tree I can sort of create bar charts, couple of bar charts. One of the bar chart sort of focuses on earlier growth, and the second bar chart in the same plot for the same tree corresponds to later growth, and we will see that how the plot looks like. So this is exactly how the plot looks like. So again on the x axis we have the different trees, so 5 in number, and on the y axis we are plotting the mean growth in millimeters. Okay. So again if you see for the first tree, the earlier growth ranges somewhere around 30 millimeters, while the later growth is not even, let's say, 5 millimeters. Okay. And this conclusion is seen across all the trees, be it 1, 2, 3, 4, 5. So surprisingly, if you see the second tree, there is no growth in the later stages. Can you see that? So there is no bar which is in blue here, isn't it? So if you don't have any blue bar here, the value is 0. And again you saw that in the frequency table as well, which means that if the tree is coded with number 2, which means the second minimum maximum diameter growth, then almost all the growth happens in the earlier stage. So 118 days to 484 days. Now the last thing is comparing tree groups. So the question here is, are some trees consistently larger than others across all time points? Okay. So here again the focus is somewhat on the circumference. Now again remember that this is a very small data set. So by small data set I mean that you have certain number of rows, but the focus variables are just 2, right? I mean one of them is age, other is circumference. So and then we are sort of discussing what all different kind of questions one can ask or rather analyze or try to find solutions for, even for a smaller data set. So we are sort of exploring different variations of analysis. Alright, so now this question is, are some trees consistently larger than others across all time points? So what could be done here? So again, I can sort of create a frequency table of average circumference per tree. So again, the idea revolves around a couple of things. So frequency tables, line plots, bar charts, histograms, etc. Okay. So I can actually use a frequency table of average circumference per tree across all the observations. Something like this. So again, the first column gives you the number of tree, or rather the notation for the tree. So 4, 2, 5, 1, 3. And again, the reason behind this ordering is that, which would be evident in the second column. So second column gives you the mean circumference of the corresponding tree, and as you can clearly see, so you have certain ordering from maximum to minimum. So what you mean by this is that the tree coded with number 4 has a larger mean circumference as compared to a tree coded with number 3 here. And by the way, the third column gives you the standard deviation. So SD stands for standard deviation, which we just talked about in the beginning of today's session. So again, here you can clearly see that the standard deviation or the variation among the observations for the tree coded with number 4 is also slightly larger, 71 as compared to 42 with a tree with number 3. And again, like I said, each tree has sample size to be 7. So overall, I guess the overall sample size happens to be 7 into 5, which is 35. Okay, so we are supposed to cover one more example. Yeah, so by the way, this is what we have done. So we have created a frequency table of average circumference per tree, and now if you want a visual sort of a plot, we can go ahead and then create a bar chart. Okay, and then what exactly would a bar chart look like? So again, on the x-axis you have different trees 1, 2, 3, 4, 5, and on the y-axis you have the mean circumference in millimeters corresponding to each tree. So again, clearly you can see that trees 2 and trees 4 show more growth in terms of circumference. And by the way, if you see these bars, right, so these bars sort of measure, they sort of extend from the median to the maximum. Okay, they sort of extend from the median to the maximum. So they sort of give you a range of how the data is spread out from median to the maximum. So again, the idea is, or rather the summarization point is, even if you have a simple data, you can attack the analysis from different angles, you can create some different problems and try to get some simple solutions rather than modeling or getting some hi-fi statistics. Things can be kept as simple as, let's say, finding mean, median, mode, creating some frequency tables, finding, let's say, cumulative frequencies, for example, relative frequencies, and then visually also drawing some simple charts, histogram, bar charts, etc. Okay, thank you.